I'm going to be talking about lamp observations of the GRAIL and the LCROSS impacts, and I want to acknowledge my lamp team members, and also to thank the LRO operations team for making this possible. They worked in a very short amount of time to plan the observations, and it was just outstanding. So the LCROSS mission was a mission that the objective was to reveal volatile constituents in the lunar PSRs. And what they did was crashed this Centaur stage of the launch vehicle into the permanently shadowed region of Cabeus near the lunar south pole. Then there was the GRAIL spacecraft, which were a pair of spacecraft that were measuring the moon's gravity. And at the end of the mission, when fuel was running out, they determined that the spacecraft were going to hit into the cell side here, which was renamed the Sally K. Wright Impact Site. Huh?
I need you your cursor that it doesn't show.
Oh, it doesn't show. Okay. So what we're going to do is compare these two impacts. There's the targets were different. One was into a permanently shadowed region, and the other was into a polar region, but not in permanent shadow. So we can compare the abundances in the target regions. And when you do that, then you can understand what the constituents of those regions, the composition of those regions are. And then the other thing that we can compare is the impact parameters and how that feeds into the vapor plume that is produced by the impact. And LCROSS was a much more energetic impact, but it was also a vertical impact and a nearly hollow impactor, which tend to impart less energy into the vapor plume than the grazing incidence and the chunky impact of the GRAIL spacecraft. So in both cases, both experiments actually had two impactors, the Centaur followed by the shepherding spacecraft, which had the instruments on it 4 minutes later for LCROSS. LAMP only saw the first one there, but for GRAIL, the impacts were separated by only 30 seconds, and LAMP saw both of those. So this shows what LRO and LAMP's viewing geometry was for the LCROSS impact. And for GRAIL, it was very much the same. We're flying over the pole of the moon, and we're looking out over the limb at the dark sky, and our field of view is up over where the vapor plume expands out into our field of view. Then we pass the impact site and keep on going. And we've used that geometry for the orbits before and after the impact. And so we got an idea of what the background stars look like, so we could subtract out the background from the previous orbits to just get what the signal was from the vapor plume. So we did that for both LCROSS and GRAIL. When we look at that signal from the plume, we integrate over the spatial dimension of the slit, and we get the spectrum. What we find is that in this wavelength range between 130 and 170 nanometers, we can fit that spectrum by, or with a combination of molecular hydrogen and carbon monoxide. And then the line that we see at 185 nanometers, we can fit with a combination of atomic mercury, calcium, and maybe a little bit of magnesium even thrown in there. Now for GRAIL, this is what the spectrum looks like, and we again got that that line at 185 nanometers, which we attribute to mercury. And the region between 130 and 170 nanometers is pretty noisy, so we have not identified any molecular hydrogen or carbon monoxide in there. But we do have an excess signal at Lyman alpha from atomic hydrogen. And that's a funny line shape there, but that is basically the known instrument response at Lyman alpha. So what we do is then we look at the counts divided up by wavelength range and get the light curve, which tells the evolution of the plume in the field of view of LAMP. Then we model it with the Monte Carlo model, which follows 100,000 particles on collisionless ballistic trajectories. And this collisionless approximation is good after the first less than a second after impact. So it follows all the times that we're interested in for our observations. Then we do multiple model runs with different initial velocities to try to determine what the velocity of the vapor plume was when it was released. So we do that by flying through to determine what the light curve would be if LAMP was flying through the model, and then calculate the chi-square difference between the observations in the model, and we can get the velocity in the math. So the velocity that goes into our model is a two-component velocity. The first component is the bulk velocity, which is radially outward. It's a constant magnitude. And then the second component of the velocity is the thermal velocity at a constant temperature. So our constituents of different masses will have the same temperature but a different distribution because the mass factors in there. So here's an example of what the distribution, the thermal component of the velocity looks like for mercury on the left and atomic hydrogen on the right. And you can see that at the same temperature, because the mass is so much different, you have a very different thermal component to the velocity. So that's going to contribute to very different looking plumes based on what the plumes are made out of. When you add that thermal velocity to the bulk velocity, you get these drifting Maxwellians, and you can see a very narrow distribution of velocity for mercury being released in the plume, and a much broader distribution of hydrogen. So this is what the model looks like for the GRAIL impact. We have a shell coming out of the mercury vapor plume from the first impactor, and then 30 seconds later, a second shell from the GRAIL B impactor. Hydrogen looks a lot different because of its different velocity distribution. The hydrogen plume is much broader, and the two signals from the two plumes overlap. It gets brighter after the second GRAIL spacecraft hits, but spatially the two signals are overlapping. So we perform our model fly-throughs, and now I'm back to LCROSS. This is our light curve from the mercury, magnesium, calcium component of the spectrum. And these are the LAMP data. And so when we use our model and we vary the bulk velocity, you can see that in order to get the vapor plume into our field of view, when we saw it, it had to have a bulk velocity of somewhere between 3 and 4 kilometers a second. And then when we vary the temperature, keeping the bulk velocity the same for different model runs, you can see that if you have a low temperature, you get a much narrower signal. And if you use a higher temperature, you get a much broader signal. So we do lots of model runs, filling up this temperature versus bulk velocity space, and compute the chi-square between the model light curve and the observations. And you can see that the chi-square is best if you have a bulk velocity between 3.5 and 4 kilometers a second, but it's pretty much independent of temperature. Temperature does not influence it very well. But then when you go to the other light curve, the one from that's comprised of molecular hydrogen and carbon monoxide, you can see that it's a much broader signal. And so we can use this information to help us narrow down the temperature a little bit better. We do the same thing, modeling the H2 and CO evolving in the plume as a function and filling up the parameter space of temperature versus velocity. And because the H2 behaves so much differently, we get a different response here. You can see that the best fits come from temperatures below 1,000 Kelvin and velocities that are between 3 and 4 kilometers a second. So here are the GRAIL observations, the LAMP observations of the GRAIL plumes. The top plot shows the signal at 185 nanometers, which was mercury, and you can see that there are two distinct peaks from the two separate impactors. And on the bottom, the hydrogen observations is the more prolonged signal, with the plumes probably overlapping, as we showed in the model before, and our very, very preliminary fits to the data show that if we use the same sort of bulk velocity, so we're between 3 and 4 kilometers a second, the timing of those peaks works well for the GRAIL observations, just like they did for LCROSS. And using the hydrogen signal, we can get an idea of the temperature, and it's looking like it's going to be something lower, around 200 Kelvin, which is consistent with the lower energy of the GRAIL impact. So work is ongoing to set upper limits for abundances and also to cross-check detections. And once we do that, we can make comparisons of the abundance of the constituents at LCROSS site and the GRAIL site. But it's interesting that mercury is common to both. Hydrogen in atomic form at GRAIL leads us to need to go back to the LCROSS observations to see if there was a signal of Lyman alpha there that we missed. But if the hydrogen's coming out in atomic form at GRAIL and molecular at Cabeus, that would be very interesting and would give us an insight into hydrogen and how it's stored in the regolith. So then we're also finalizing the, hold on, my timer just went. So we're finalizing the velocity simulations for GRAIL, but even though it seems like the GRAIL impacts had a lot less energy, the Plumes came out with about the same bulk velocity, but a lower temperature. So once we do a little bit more work, it will help us understand kind of how the difference in the impact parameters contribute to the properties of the vapor plume. So that is what I have.
Great, thank you so much. Okay, Carly, are you monitoring questions? We still have Carly?
I haven't seen any on the screen yet. If people want to type in questions or raise their hand. Let's see. One from Leslie Grush. Do you have a preferred explanation for the mercury activity between GRAIL A and B impacts?
I'm not sure what you mean by the GRAIL activity. Do you mean that the peaks were slightly, or that there was a sharper fall off in the model than there was in the data? Or, I mean, so the mercury, I think, wasn't unexpected at the GRAIL A and B because there's some...
So it's not the peaks, but the signal between the impacts did not match the model.
Yeah, I mean, I think that we're getting close. That's down in the noise, is that signal in between, but we can change change the temperature, which I didn't do a whole lot of, and increasing the temperature will broaden that peak if we find that gives us a better fit. But as Kurt's typing in, that that is a very noisy signal there. The GRAIL impacts were much smaller than LCROSS, and so the signal to noise just isn't as good.
Okay, and it looks like there's one more question. How sure can we be about the contribution of the impactor to the plumes released following the impact?
That's a really good question, and you know, that's something where we need to know what the spacecrafts are made of. For the LCROSS experiment, because the whole objective was to understand the volatile contents of Cabeus, they took great effort to try to make sure that all the fuel had been baked out of the Centaur before it hit. The GRAIL things, they also tried to burn off the fuel. But, you know, we did see amounts that are much higher than anything we expected to be in the spacecraft themselves. So there was something originating from the moon. So what's Kurt saying? Kurt says Zuber's team did an analysis and they can't account for any HG at all. So no mercury in the spacecraft. And there's potentially hydrocarbons, so, in the GRAIL impact.
Okay.